There's this image we all have of modern science. It's almost cinematic.
Mm.
We picture some massive, sleek, supercomputer, like Frontier Summit humming away in a big cold room.
The blinking lights, the whole deal.
Exactly. And we think, okay, we have the raw power. We can simulate anything. Airflow over a jet, protein folding, a whole galaxy evolving.
It's a really seductive image, isn't it?
Yeah.
The idea that brute force computation is the ultimate hammer for every nail.
It is. But here's the thing that's actually kind of surprising, something we found digging into this for today's deep dive. You can have the biggest, most expensive hardware on the planet.
Hundreds of millions of dollars worth of silicon.
And if you feed it a math problem that is, let's say, messy or poorly shaped, that supercomputer will just choke.
Oh, choke is putting it mildly. It can spin its wheels for weeks, maybe years,
Yeah.
on an equation that, theoretically should take minutes.
And the thing that saves us, the thing that turns that year-long wait into like a lunch break, it isn't a new chip. It isn't quantum computing.
Yeah.
It's a piece of math. A specific kind of matrix transformation called a preconditioner.
The unsung hero of computational science. It really is the difference between getting an answer and just an infinite loop.
So today we are diving deep into the art of the shortcut. We're looking at how mathematicians turn these impossible knots into straight lines, why step 0 is the most ignored safety rule in engineering, and how a specific magic trip involving Pac-Man makes image processing possible.
And to really get any of this, we have to start with the boss fight of computational science. The single equation that, effectively runs the entire engineered world.
S is bound by X.
X is beta baller. It looks so simple,
Mm-hmm.
so innocent.
Right. It looks like something you'd solve in middle school. If A is 5 and B is 10, then X is 2. Done.
If only. In the real-world fluid dynamics, structural engineering A isn't just one number. It's a matrix.
A huge one.
And not just any matrix. We're talking about a grid of numbers with potentially a billion rows and a billion columns.
A billion by a billion. That is a spreadsheet from hell.
It is. And X is the state of the world you're trying to find, the temperature at every single point in an engine, or the pressure on a wing. And B is the force you apply.
Okay.
The problem is you can't just, divide by A.
Right.
Converting a matrix that size, it's computationally impossible. Literally, it would take more memory than exists on Earth and more time than the age of the universe.
So we guess.
We guess. We use what are called iterative solvers, algorithms with names like conjugate gradient or GMRES.
They sort of walk towards the answer.
They do. They take a guess at X, see how wrong they are, and then adjust. They're trying to walk downhill to find the lowest point, which is the solution.
Like playing a game of hot or cold.
Precisely. But here is where the preconditioner comes in. The game of hot or cold only works if the terrain makes sense. If the problem is what we call poorly conditioned, the solver just gets lost.
Let's unpack that term. Poorly conditioned. This is
Thank-
kind of the villain of our story today.
The villain is the condition number. It's
Mhm.
usually denoted by the Greek letter kappa.
What does kappa actually measure?
Think of the solution space as a landscape. If kappa is low, so close to 1,
Right.
that landscape looks like a perfect round bowl.
Okay.
No matter where you drop a marble, gravity pulls it straight to the bottom. That's the answer. The solver gets there in a few steps.
And if kappa is high,
Then the landscape is warped. It gets stretched out into a long, incredibly narrow, steep valley with a really flat bottom.
so if you're the marble.
You don't roll down. You just
Yeah.
rattle back and forth against the steep walls.
Mhm.
You zigzag. You take millions of tiny steps, bouncing side to side, but you never actually move forward along the valley floor.
And in real physics, like modeling a car crash, how high does this number get?
Oh, huge. 10 to the 8, 10 to the 12. The valley is effectively infinitely long and narrow. The solver stalls.
Mhm.
The fans are spinning, but the air isn't going down.
So the preconditioner, it doesn't solve the problem directly. It changes the landscape.
That is the key insight.
Mhm.
We don't solve X B ball. We multiply both sides by a new matrix, M or inverse. We solve M1X, M1B.
And if M is a good preconditioner,
Then it acts like a lens. It squashes that long, narrow valley back into a nice, round bowl. Mathematically, we say it clusters the eigenvalues.
I love the visual one of our sources used. It's like you have a scattered crowd of thousands of people in a stadium, and you need to get them all through one door.
Right, total chaos.
And a good preconditioner is like organizing them into a perfect single file line before they even get to the door.
That's a perfect analogy. The solver suddenly sees a straight line and just sprints to the answer.
Okay, so we want this magic matrix M. We want to organize the crowd. But before we even open the toolbox to pick a method, the research highlights this critical, often ignored first step. They call it step zero.
Step zero, scaling, or uh, equilibration.
The eat your vegetables phase of linear algebra.
It really is. Because everyone wants to skip to the complex algorithms, the dessert. But if you skip scaling, nothing else you do matters.
Why is it so critical?
Okay, imagine you're simulating a bridge. You measure the length of the bridge in kilometers, but you measure the thickness of the rivets in millimeters.
So in your matrix, you have a number representing kilometers, which is small, next to a number for millimeters, which is huge.
Exactly. You might have 0.001 right next to a million. Computers hate that. Floating point arithmetic has limited precision. When you mix tiny, huge numbers, you get rounding errors.
And those add up.
They accumulate, and your condition number explodes just because of your choice of units.
So scaling is just leveling the playing field.
Yes, you multiply the rows and columns to make sure every entry is roughly the same size. And there's this beautiful piece of theory here. I love van der Sloos's theorem.
Van der Sloos's, it sounds like a spell from Harry Potter.
It's better than a spell.
Yeah.
Van der Sloos proved that if you scale the matrix so that every row has a unique Euclidean norm,
So making the length of every row vector equal to 1.
yes, if you do that, you're mathematically near optimal for minimizing the condition number.
So you don't need a complex algorithm, you just normalize the rows.
And it is so cheap. It costs almost nothing in compute time. But if your data varies by a factor of 1,000, which almost all engineering data does, it's mandatory. If you ignore step zero, your fancy preconditioner is just fixing a problem that you created.
Okay. We've eaten our vegetables, the matrix is scaled. Now we face what the sources call the trilemma.
The optimization trilemma.
Yeah.
Yeah, this is the framework for choosing a preconditioner. You have three competing forces, and you can almost never have all three.
Let's list them.
1. Conversion speed. How few steps does it take to solve?
Okay.
2. Iteration cost. How expensive is it to calculate each one of those steps? And 3. Parallel scalability.
And that last one is the big one for modern supercomputers. Can I run this on 10,000 GPU cores at once without them all waiting on each other?
And the answer is almost always pick 2.
So let's look at the arsenal of options, keeping that trilemma in mind. Let's start at level 1, the simple stuff.
Pointwise methods. This is where you start with the Jacobi preconditioner. It's the simplest possible idea. You look at your massive matrix A, you take the numbers on the main diagonal, and you throw everything else away. Your M is just the diagonal.
That seems reckless. You're tossing out 99% of the information.
You are. But remember the trilemma. Jacobi is incredibly cheap. It's trivial to invert. And crucially, it's perfectly parallel. Each row is independent.
Does it actually work?
It works surprisingly well if your matrix is diagonally dominant. That just means a point's interaction with itself is stronger than with its neighbors. If that's true, Jacobi's great. If not,
It fails miserably.
utterly. So we move to level 2. The workhorses. Incomplete factorizations.
ILU.
ILU, incomplete LU.
Yeah.
This is the bread and butter of scientific computing.
Now, normally to solve a system directly, you do Gaussian elimination. You factor the matrix into triangles.
Right, but that creates fill-in. A sparse matrix, one that's mostly zeros, becomes dense. You run out of RAM instantly.
Ah.
So ILU is a compromise that says, let's do the factorization, but whenever we create a number that's small or in a spot that was originally 0,
Well,
let's just throw it away.
it's like saving a high-resolution photo as a compressed JPEG. You lose some detail, it looks a bit fuzzy, but the file size is manageable.
That's a great analogy. You have variants like ILUT, which uses a drop tolerance. If a value is smaller than, say, 10 to the minus 3, you drop it. It keeps the memory footprint low.
This sounds like the winner. It balances accuracy and memory. But looking at our trilemma, I see a massive problem with point 3, scalability.
That is the Achilles heel. Solving a triangular system, which is what you do with ILU, is inherently sequential.
Meaning what?
To know the value of x2, I need to know x1. To know x3, I need x2.
It's a domino effect. You can't knock down the last domino until the first one falls.
Exactly. So if you have a massive GPU with thousands of cores, 99% of them are just sitting there waiting. It bottlenecks the whole system.
So ILU is great for a workstation, but maybe not for the Summit supercomputer. Which brings us to level 3. Go big.
This is where we talk about AMG, algebraic multigrid.
The industrial strength choice.
If you are simulating something like an engine block or a complex geological formation, an unstructured grid, AMG is usually the best answer.
How does it work? It sounds like magic.
It thinks hierarchically. It looks at your fine grid, all the tiny details, and it automatically builds a coarser version of the problem, that a coarser version of that.
So it solves the easy local parts on the fine grid and the big picture error on the coarse grid.
Exactly. It attacks the error at every frequency at the same time. It's incredibly efficient in terms of iteration count,
Mhm.
but it is heavy. The setup cost is high. And coding it, forget it. It's a black box.
But what about that GPU problem? If ILU is too sequential and AMG is too complex for a GPU, what do we use on the new chips?
We look at SPAI, sparse approximate inverse.
This one flips the script entirely.
It goes. Instead of trying to factor A, SPAI asks a different question. It asks, can I find a matrix M such that M times A is close to the identity matrix?
It tries to build the inverse directly.
An approximate inverse, yeah.
Yeah.
Minimizes the error.
And why is that better for parallel chips?
Because applying SPAI is just matrix vector multiplication. Every row can be computed independently. No domino effect, no weighting. You can light up every single core on a GPU at the same time.
Okay, so if I'm summarizing, Jacobi for the simple stuff, ILU for general purpose on CPUs, AMG for the heavy lifting on messy grids, and CBAI for the parallel GPU era.
That's the general taxonomy.
But there's always a but. Sometimes the matrix isn't just a random mess of numbers. Sometimes it has structure.
Beautiful repeating structure. And if you spot that structure, you can cheat.
Let's talk about signal processing and image reconstruction. The source material brings up Toeplitz matrices.
A Toeplitz matrix is a very special creature. It has constant diagonals. So if you look at the main diagonal, every single number is a 5. The diagonal next to it, every number is a next to 2, and so on.
And this happens a lot in time series data, right? Because the system's behavior today depends on yesterday in the same way tomorrow depends on today.
Exactly. It represents shift invariance. It's like an echo. Now, solving a generic Toeplitz system is expensive. It's order n squared complexity. Double the data, the work quadruples.
But mathematicians found a cheat code, the circulant matrix.
This is where the magic happens. A circulant matrix is like a Toeplitz matrix, but it wraps around. The end of the row connects back to the beginning.
Like the world in Pac-Man, if you go off the right side of the screen, you just appear on the left.
Precisely. And because of that Pac-Man geometry, it turns out that any circulant matrix can be perfectly diagonalized by the fast Fourier transform, the FFT.
Okay, for the listener who isn't doing Fourier transforms for breakfast, what does that mean for speed?
It means we can turn a difficult matrix inversion problem into a simple multiplication problem in the frequency domain. It drops the complexity from O(n) squared down to n log n.
To put that in perspective, if you have a huge data set, that is the difference between an answer in 10 seconds versus an answer in 10 days.
Or getting an answer at all.
But here's the snag. Our real data, the Toeplitz matrix, isn't a circulant matrix. It doesn't wrap around, the echo eventually fades, it doesn't loop. So how do we use the cheat code?
We try to find a circulant matrix C that's close enough to our Toeplitz matrix A, and then we use C as the preconditioner.
And this brings us to a specific hero mentioned in the sources, Tony Chan.
Yes, 1988. This is a classic moment. Before Chan, people like Gilbert Stranger proposed chopping off the corners of the matrix to force it to wrap around.
Brute force. If it doesn't fit, cut it.
It worked, sort of, but it wasn't elegant. Tony Chan asked a different question. He asked, what is the circulant matrix that is closest to my matrix A in the Frobenius norm?
The Frobenius norm being a way to measure the distance between two matrices.
Correct. He wanted the mathematical soulmate of the matrix, not just a butchered version. And he solved it analytically. He found a formula that averages the diagonals of the Toeplitz matrix to construct the optimal circulant approximation.
So instead of just chopping data, he found the mathematical best fit.
And the result was robust. Strang's method sometimes failed. Chan's method worked even for non-symmetric matrices. It was just a beautiful example of finding an optimal mathematical compromise.
It really highlights that this field isn't just about crunching numbers harder. It's about looking at the shape of the problem. Is it a valley? Is it a Pac-Man world? And finding the key that fits that specific lock.
Absolutely. You're matching the physics to the math to the hardware.
So we've covered the theory, the taxonomy, the magic tricks. Let's get practical. If I'm a listener with a massive linear system to solve, how do I actually choose? I don't want to derive Chan's formula by hand.
Please don't. No, we can break it down into a decision matrix based on the source guide.
Okay, let's role play. Scenario 1. I'm simulating airflow on a nice structured grid.
Geometric multi-grid, don't overthink it, it's optimal. As you add more grid points, The number of iterations stays constant. It is the gold standard.
Scenario 2. I have a total mess. Unstructured mesh, complex geometry, weird material properties.
AMG, algebraic multigrid. It's the tank. It will just roll over the problem. It might be heavy, but it will work.
Okay. Scenario 3. I'm on a massive GPU cluster, and I need to keep thousands of cores busy without them talking to each other.
Block Jacobi, or SPAI. You sacrifice a bit of convergent speed per iteration. You might need more steps, but you make up for it by doing millions of those steps per second because there's no communication wait time.
And finally, what about the tricky stuff? Saddle point problems, like Stokes flow where you have velocity and pressure coupled together.
Ugh, those are nasty because they're indefinite. The matrix has positive and negative eigenvalues.
Yep.
Standard methods fail. You need specialized block preconditioners like PCD. You have to respect the physics of the coupling.
And the good news is we don't have to code these from scratch.
Oh, God, no. If you're coding these from scratch, you're either doing a PhD in numerical linear algebra or you are just wasting your time. Use the libraries. PAT is the gold standard. What makes it so brilliant is that it abstracts the math away. You write your physics code once, and then you can swap out preconditioners with a single line of command line code.
So I can try ILU, realize it's too slow, then switch to AMG, then switch to Jacobi, all without recompiling my code.
Exactly. It turns the art into a rapid experimentation process. I mean, there are other great tools like Trollinos and Hypre, but the principle is the same. Don't reinvent the wheel. Be the architect, not the bricklayer.
I like that distinction. So, pulling this all together, we started with the idea that raw power just isn't enough. We need these shortcuts.
But they aren't really shortcuts, are they? They're transformations. They're about understanding the underlying structure of reality, the smoothness of a fluid, the repeating pattern of a signal, and mathematically reshaping the problem to expose that structure to the computer.
It's surprisingly philosophical. It's about translation.
It is. The main takeaway for me is that there is no single best preconditioner. It's an art form. You're balancing the trilemma. You're balancing physics, math, and hardware.
And speaking of where this is going, there was a note in the advanced topics section that gave me pause. We've been talking about the human art of selection, but what about AI?
Machine learning for preconditioning. This is the frontier.
Right now, choosing the drop tolerance for ILU or the coarsening strategy for AMG it's a guess. It's trial and error, human intuition.
But now researchers are training neural networks to look at the matrix patterns and predict the optimal parameters, or even to learn the coarse grid operators directly from data.
So here's the provocative thought to leave you with. We've spent this whole deep dive talking about the insight required to pick the right method, matching the key to the lock. Are we moving toward a world where the math solves itself? Where a neural network understands the structure of your physics simulation better than you do?
It's a fascinating possibility. We might eventually just treat the solver as a true black box. But for now, understanding that kappa, that condition number, is still the difference between an answer and an infinite loop.
The machine still needs a human to tell it how to learn. For now. Thanks for diving deep with us into the mechanics of making math fast.
It was a pleasure.
We'll see you on the next one.